All right. Hello, everyone. Welcome to UTMIST Academics, one of our first workshops, or I guess second workshop if you came to the IEEE one earlier this year. My name is Jessica. I'm co-VP Academics this year, and we're really excited to be introducing these series of workshops to you guys for you, everyone, regardless of your skill level or your familiarity with machine learning, to introduce these topics to you. The first one that we have is a classic that this is the third year that we've been running this. Reinforcement learning. We'll be giving an intro later as well, but this topic has been presented at our workshops for 2 or 3 years now, and we're happy to bring this back. And I guess I'll pass it on to Jingmin, our academic director, who's going to be leading this workshop.
Thank you, Jessica. Okay, hello everyone. This is Intro to Reinforcement Learning. I'm so happy you could make it out here tonight at this late hour. Before we get started, of course, here's our land acknowledgement. And then I always like to do something before we start every workshop. It's like talking about the news and AI, because after all, we're all interested in AI. We all want to know what's happening, right? So every workshop we're going to start with this. So this is just some AI news that's came out recently. OpenAI and NVIDIA have signed a letter of intent for $100 billion partnership. So this field. Oh, since you're all here, I probably don't need to convince you about AI, right? You're interested in AI, but this is a very burgeoning field that is the future. Also, I just read recently, it's not on here, but NVIDIA actually solved some physics simulations, the most accurate physics simulation that's ever been done. So yeah, please check that out if you have time. It's just really cool. AI regulation. Now with AI, right, you need to regulate it, otherwise we're all going to get replaced. So yeah, California could be the first state to regulate AI if Bill SB 53 is passed. And this has been a really big field as well, AI safety, AI regulations. So if you guys are interested in that, I know I am. Please feel to check that out. I believe we have some workshops in the future as well. And finally, upcoming UTMIST, right? Our club is the premier artificial intelligence club in Canada, maybe in North America, who knows? And every week we have machine learning fundamentals from 1 to 3 p.m. That's for actual introductory AI stuff. I highly recommend you check it out. We have paper readings. So I mean, AI research is all about reading papers, and we have that every Saturday from 3 to 6 p.m. And this is what we're most excited about: AI Squared. It's a reinforcement, not just reinforcement, but machine learning tournament that will be happening soon. And this course is a very nice introduction to that, because you'll probably be using reinforcement learning in that. So yeah, very exciting stuff happening. And if you're in UTMIST, you're in the right place. So before we get started, can I just get a show of hands? Who here is a first year? Okay, great, awesome. Second year? Okay. Third year, fourth year, and above? Okay, great, awesome. Just for me to get an idea of who knows what. Who has done AI before? Neural networks, gradient descent, backpropagation, and any of that? A little bit? Okay, not everyone. Okay. Good news. So actually, if you haven't done that, I'd recommend checking out the machine learning fundamentals. But good news for reinforcement learning, as you'll see, you actually, well, at least for our lecture series, okay, in the future maybe, but for right now, you actually don't need any of that. For all that gradient descent, backpropagation, all that, neural network stuff, you actually don't need any of it, because as we'll get into, reinforcement learning is a brand new sort of, not brand new for you guys, but it's a whole different paradigm from traditional machine learning. And by tradition, I mean neural networks and stuff. So yeah, it's actually, you don't need any of that background. But before we get into that, just some administrative stuff. So I'm Jingmin. I'll be presenting. Time and location every week for the next, I think, 4 weeks. In here, no, wait, in Bayonne from 7 to 9 p.m. And yeah, we'll be covering RL. And I highly recommend you. I know this is gonna happen for sure, but you guys are gonna not come to the next one, because that's how just university lectures go. But I highly recommend you guys keep coming for the 4 weeks, because the good stuff happens at the end, right? So yeah, please do come, and yeah, I hope you guys learn a lot. So so here are the prerequisites for reinforcement learning. Approximately none. Now that approximately has a pretty big emphasis on it. It'd be nice for you to have some math background. But genuinely, like as I said before, if you've not done AI before, this is a very different paradigm than traditional neural networks and all that. So it's good that you don't need like all that complex stuff. So just coming here with an open mind, and I hope you guys learn a lot, and I hope you guys have a genuine passion for the subject, because that is definitely what is required. Okay, let's just get started. So here's the overview of reinforcement learning. How many of you have like heard about this term before, nebulously? Okay. Okay, great, great. So I mean, I bet you guys have seen this diagram before. If you guys take an AI course, right? It's called like the three branches of machine learning. You know, if you go take an AI course at UofT, you'll definitely see this. The professor will say, okay, guys, so there's three branches of machine learning. There's supervised learning, there's unsupervised learning, and there's reinforcement learning. And what will happen is the prof will say, this course, we're going to cover supervised learning and a little bit of unsupervised learning. Reinforcement learning, we won't cover. We'll leave it for another course down the line. But actually, there's basically no courses down the line that cover this. So they kind of lie to you, especially if you're engineering. Like there's basically zero. There is a course called Adaptive Control and Reinforcement Learning. But wow, I don't recommend you guys take that. It's extremely difficult. So yeah, so this is a very like nice introduction to reinforcement learning. And you'll get stuff that you probably won't learn in a lot of your courses. Because I'll leave the supervised learning and unsupervised learning to your courses, or maybe the other workshops in UTMIST. Now, reinforcement learning has many faces, right? I mean, it's not just an AI algorithm, right? It encapsulates many things. It's about making decisions, and when do you have to make decisions? Well, everything, right? Whether it's machine learning, whether it's psychology, whether it's neuroscience, whether it's engineering, all of these things, all these fields, you have to make some decision, right? Based on a reward signal or based on your preferences. And that is really at the heart of reinforcement learning. So I just want you to know that reinforcement learning doesn't just, or at least the thought process behind reinforcement learning is not just limited to AI and machine learning. It's, extremely multifaceted, and it's really present in any other field. The principles in reinforcement learning really apply to many, many fields you'll encounter later on. So it's a very nice thing to learn. Now, let's just give a quick definition out of the way. I've been dancing around this word for a while. What is reinforcement learning? So reinforcement learning is when an agent, okay, interacts over some period of time with an environment in order to achieve a goal. Okay, now those terms are highlighted because we'll define them later. But basically, the agent should be able to sense the state of the environment most of the time, and have clear goals relating to the state, like stuff they want to achieve, right? And most oftentimes, the goal will be to maximize something called the return, which will be discussed later. And by the way, if you guys have any questions at any point, just raise your hand. Now, I mean, putting aside these technical terms for a minute, you'll see that this is a very sort of, I guess, a familiar situation, right? I mean, every day you guys do tasks, interact with the environment around you, and to achieve a goal, whether it's, making dinner, coming to school, getting an A on the next assignment, whatever, right? So this concept should be very familiar to you guys. But the key question here now becomes, how do you make a machine do it? How do you make an agent or like something that's not you, that's not living, do the same things that you do, and how make good decisions, right? That's really at the heart of reinforcement learning. Now, what isn't reinforcement learning? Okay, now if you came in here expecting, for those of you with some AI background, right, maybe I'll pull up some architecture on the screen. Maybe this is a variation of some transformer, right? No, right? Reinforcement learning is a whole new way of thinking, a whole new paradigm. Okay, it's not like, okay, here's this architecture, here are the hyperparameters, here's how you train it, and you're done, right? Like GANs or something, right? No, this is a whole new way of thinking, and I hope you get accustomed to this. We'll not be delving into, okay, so the implementation details here, like, okay, so this is how you instantiate a layer, the layer needs to have this. No, it's a way of making agents make decisions, and I hope you guys understand that. Now, examples of reinforcement learning. Reinforcement learning, in my opinion, is one of the most magical fields in machine learning because it most concretely, reflects what us as humans do, right? For example, here, AI learns to escape reinforcement learning. Now, this is a very popular YouTube channel called AI Warehouse, and one of our former co-presidents actually works here. And it's very cool because it teaches these little agents to do certain human-like tasks, right? Like maybe escaping a room, learning to run, etc. How would you use a mathematical model or a traditional neural network to do that? Maybe think about that for a minute. Right, so reinforcement learning can do these things that are very human-like, which I find very interesting. DeepSeek, I think ChatGPT used to be here, but it's not replaced with DeepSeek. But yeah, both models are trained using reinforcement learning. Now you might be thinking, okay, no, ChatGPT is a chatbot, it's trained using a transformer using a large language model. Yes, that's true, but at the end, right, they do, I believe, reinforcement learning with human feedback. Maybe you guys have heard that, where they make the answers like not racist or something. So that's so reinforcement learning is everywhere, even the places you think it's not. Okay. And AlphaGo, I mean, this is really interesting. Have you guys heard of AlphaGo? It's where like a reinforcement learning program was able to beat the top Go player in the world. Now think about yourself. How would you write a program to do it? Like that's impossible, right? But reinforcement learning can. So this is why where you can see the power of reinforcement learning and why I think it's so important to learn it. And just a little bit more motivation. So let's say you're playing this game. I think it's called Blocks Buster or something in Atari. How would you write a program to do this? For you guys who don't have any experience with AI, ignore the supervised and unsupervised part. How would you write a program to do this? Right? I mean, just think about it. Like you have to capture every single pixel. And every single pixel, there's a corresponding robot movement, and maybe you have to consider future time steps as well. I couldn't even imagine how to do that, right? Like maybe you need like 100 million if statements if you want a program to do this, right? So it's very hard, but reinforcement learning, as we'll show, can pretty easily, readily solve problems like this. And okay, so what makes reinforcement learning different from other machine learning paradigms? Goal is to maximize reward signal. Now, the reward signal is not that present in other machine learning paradigms if you have done AI before, right? There is a loss function, and I guess that could be counted as kind of like a reward signal, something you want to maximize or minimize, but it's not quite the same. Feedback is delayed, not instantaneous. So if you pass a training example through a model, you'll get a loss signal, right? You get a loss function number, you get a number, and you can backpropagate through that and get a feedback right away. But reinforcement learning, sometimes that's not the case. Sometimes you need to wait. You need to interact with the environment, collect, transitions, collect experience, and then make the best decision based on that. Okay, and this is very important. The third point is very important. The actions of an agent affect the environment, right? Like if you, let's say, move a desk somewhere or you do something, right? The desk will be moved, right? There's an effect on the environment. Whereas in regular machine learning or supervised learning, you have a fixed data set, right? Nothing happens, nothing moves, right? You can use it over and over again. And finally, data is sequential, not independently and identically distributed. So, I mean, for those of you without this background, just know that like in reinforcement learning, right? It's very related to the third point. You make a decision, right? The data you collect at the next time step will depend on the data you collect at the previous time step because the environment changed, right? But in regular machine learning, right, supervised learning, the data is something called, they're independent, right? One sample is like not really related to the other sample. That's really how, maximum likelihood estimation, how traditional methods kind of work, right? But you don't have to worry about this for now, the technical stuff. I just want to highlight again, though, like how similar is this to everyday life, right? When you are, walking around doing stuff, you touch things, you move stuff, you make decisions. This will affect your world, right? The actual environment, the world we're living in. Is that very similar to reinforcement learning? Feedback is delayed. Sometimes you make a decision, you think it's a good decision right now, and then later you realize, actually, wait, no, I shouldn't have made that decision. That was a bad decision, right? That's also very similar to reinforcement learning. Feedback is delayed, not instantaneous. And it is sequential. I mean, in our lives, right? We make decisions, we collect data, and the future things we see depend on the things we've seen in the past, right? So I just want to like hammer home again just how similar reinforcement learning is to your human life. And a lot of the times, I think a lot of the intuition you have for real life can be applied to reinforcement learning. Okay, so that's like it for the introduction. Before I move on, are there any questions for now? Clear? Everyone's clear, right? Okay, great. Once again, if you have any questions, please feel free to speak up and ask. Now before we dive into anything too deep, let's talk about the K-armed bandit problem. Now this problem is, okay, this joke has been on here for like 3 years. I think I should remove it. It's kind of lame. But so they're bandits, get it? Right? Like, it's pretty, okay. This just serves as a motivation to the K-armed bandit problem. What is it? So let's say you're in front of some slot machines. Okay, you have three machines. Okay, and you're a gambler. Now, don't gamble, but for this situation, assume you are. And each one has a different reward function, meaning that underneath each machine, there's some secret payout function, right? You want to gain as much money as possible. And by pulling these slots, these levers on these slot machines, you'll get some money. So what machine should we choose to get the highest money, highest reward? In the beginning, how would you do it? Like, you have no idea, right? Like, you don't know how much each machine is going to give. So maybe, so let's set the stage first, right? So just to sort of mirror the terminology in reinforcement learning, right? Agent would be you, the gambler, right? The environment are the slot machines you have in front of you. The action is choosing which slot to pull, and the reward is the money that you've gotten. Okay, and of course, like I said, even though you don't need too much math is unavoidable in machine learning. So we got to formalize this a little bit. So let K be the number of bandits or arms each slot machine. So by the way, this is why it's called a K-armed bandit problem. There's 3 slot machines. Each one's called a bandit. Okay. And each game consists of T turns. So you can pull like a lever like T times. Let A denote all the possible set of actions in the game, meaning that each action corresponds to you pulling a different machine, right? At time step T, let the action chosen be denoted by A sub T, right? And let the reward from said action be denoted R. So after you pull a machine, you'll get a reward back. You get some money back, okay? So if we have A, we can write its expected reward as this, right? It's the expectation of the reward given that at time T, you'll pull the lever A. Or just think of it as basically just how much reward you get. This is just a sort of function telling you how much reward you get, right? And the goal is to maximize the expected reward, maximize how much reward. But how do we estimate this? So we could do something called a sample average. It sounds fancy, but basically it's just the mean. You guys have heard of the mean before, right? From high school and stuff. It's just an average, right? Why not just let's think about this as an example. If we pulled the slot machine like I guess T times, right? Why don't we just average the reward we got from each machine? That's pretty simple, right? And very easy to calculate. So let's see an example of that. Okay. So let's say it's machine 0, right? At time equals 1, you pull it, right? You get 90 reward or $90 or $90 million. At time 2, you get another 90 reward. So what is the average, right? It's just 90 plus 90 over 2 equals 90. Simple enough. And guess what? This can act as a sort of estimate of how good this machine is, right? Because, it's experience. You've pulled it 2 times, you've seen what it gives you, so you have a kind of a good idea of what this machine does. Okay, so do we need to keep track of all prior rewards? And this is just a little bit of math, but it's not important. It's basically just some computational thing to make it easier. But basically, this is still taking the average. It looks pretty, different, but just think of it as taking the average. Okay. The point is that to calculate the average at the next time step, you just need the average at the current one. You need to keep track of all previous rewards. You don't need to understand this. Just think of it as taking the average. So now we can do this for all machines. So let's say some time has passed. We pulled a bunch of these machines, and these are the averages we have for these machines, right? There's a key concept in reinforcement learning called exploitation and exploration. Exploitation means you want to improve short-term benefits. Exploration means you want to improve knowledge for long-term benefit. Basically, think about this, right? Let's say you have these 3 machines in front of you with these averages, so your estimate of how good each machine is. Which machine should you pull right now? Does anyone have an answer for that? Like, which machine do you want to pull? Yeah, go ahead. You want to pull machine 1, right? Because it's got the highest reward. That would be something called exploitation, right? You want to take advantage of what you know to be the best choice right now. But there's also exploration, What if, let's say, at the next time step, right? The next time you pull, you decide not to pull machine 1, but you pull machine 0. And machine 0 gives you like, a million reward, right? Then what now, right? It means that you thought machine 1 was the best, but actually machine 0 is better. But without trying to pull machine 0 more times, you may never know. Or same with machine 2. What if machine 2 has a 0.1% chance of outputting a billion reward? You will never know unless you pull machine 2 many more times, right? So this is the trade-off here. And this is like real life. Sometimes you want to make the decision, right, that maximizes your immediate benefit. But sometimes you want to try other things, which might be a worse option now, but may lead to better options in the future, right? So this is kind of what we said, what I talked about. You might want to be greedy, right, and pull this, right? Or you could, do this. You could explore, right? So this is once again some fancy math notation, but what it's basically saying is at this current time t, you can either go with your highest option, the max, right? The max with some probability, or with some other very small probability, you pick a random action. You pull machine 0 or 2 from before. You don't go with machine 1, you go machine 0 or 2. And why would you do that? It's, as I said before, perhaps machine 0 and 2 actually have better reward, right? But you would never know if you never try it. This is just some algorithmic stuff. I don't think it's very important right now. So why did I just do that with you, right? It's just to get these sort of concepts in your head, right? Don't get too caught up in the math, in the symbols. Just basically think about this. RL is about making decisions, and you need, first of all, an estimate of which decision is the best, right? Given a state, you need an estimate of what you want to do next. That's one. Number two, sometimes, okay, you need to be greedy. You need to pick the best option right now. Sometimes you might want to explore. Okay, these are three key things. And just to sort of recap, the estimate of the reward is what I talked about before, right? The sample average, taking the average of the number of the rewards that you have attained from this machine. That's an estimate of the reward of that machine. Greedy would be picking machine 1, right? It would be like seeing this is the highest reward and pulling it. Exploration would be picking machine 0 or 2. Does that make sense to everyone? I mean, once again, you can use your intuition for everyday life here, right? Sometimes you want to make a worse decision now that might benefit you in the future. Now, before we move on, that problem was interesting, but you might have thought, okay, well, like, that's pretty simple. That's pretty simplistic. And you're right, it is. Does everyone have an idea, like, what's sort of not realistic about that scenario? Like, recall before when I talked about the characteristics of reinforcement learning. Which of these things do you think it doesn't satisfy that situation just now? So any idea? Okay, so notice the third one. The actions of an agent in its environment affect the subsequent observations it achieves. Is that really true here, right? Because in the KR-Banner problem, the state, the environment never changes. You're sitting in front of the slot machines, but the slot machines are always there. You don't move anywhere. The slot machines they don't go anywhere. The environment just never changes. Even when you pull slot 0, that has no effect on your future states, right? Because you still have 3 slot machines there. So that's very unrealistic. And that is not really what RL is about, right? If RL were this simple, then it'd be great, but not very interesting. But thankfully, RL can tackle more interesting problems because states change, and we have to consider that as well. Okay, so let's talk about this scenario then. Let's say you're a student at UofT, right? And this has happened to me. It's a personal anecdote. You just finished the class, and you see like you have 2 hours or something before your next class. You can either go home and take a nap, or you can go and study. And let's say going home to take a nap gives you 10 reward, and going home to study, or rather staying here and studying, gives you 1 reward, right? Which one would you choose? I knew which one I did. I definitely went home and took a nap, right? Because it gave you lots of reward, right? You want to be rested up. But keep in mind, right? Actions influence future rewards, right? This is not like the slot machine anymore. When you go home, when you take that action of going home, your environment's changed. You're no longer at school. You're at home, right? So this is what's different from all RL problems and the bandit problem just talked about earlier. When you take an action, your environment changes, right? And this will in turn influence future rewards. What do I mean by that? Okay, you went home and took a nap, but you overslept. Okay, because of course you did. And then you're late to your next class, or in my case, you just say, okay, screw it, like whatever, I'll just catch up with the lecture notes later, and you just stay home, you miss the class. But that's bad, right? Because now you're behind. So that gives you negative 20 reward, right? So what happened here? If you stayed and studied, you would have went your next class and you got a reward of 1. If you went home, took a nap, and you missed your next class, you would have achieved a total reward of negative 10. So it's obvious which option you should have taken, right? You should have stayed home, or rather, you should have stayed here and studied. Does everyone get my point about how actions influence future rewards and states change? Not everything just static, a bandit problem. Right? You pull the lever, nothing changes. Things change. You have to consider these future changes. The immediate best option might not be the overall best option. Now, you might be thinking, okay, like this pattern here, I get it, right? Here, if you just look at the plus 10 and you maximize that, right? You go for that, you're screwed, right? Because you get a negative 20 reward. So what is this like? What is the total reward, right? What is this term, right? In reinforcement learning, we call this the return, okay? The return is basically the total discounted reward from time step t. Basically, you start in time t, you start here, and what is the total reward? The sum of all the rewards you get at future time steps until the end of this episode or the end of this experiment or whatever. Okay, this is something called the return. And we want to maximize this, right? Because it considers everything in the future. You don't want to maximize the 1-step reward, right? The immediate reward. You want to maximize this. Now, I'm maybe thinking, okay, what is this discount factor? Or what is this like gamma symbol here? The gamma signal is basically, it accounts for the priority of long-term rewards versus short-term rewards. So let's say, okay, gamma equals 1. That means you want to consider all future rewards equally. The reward you get in the future is as important as the reward you get now, right? Can everyone see the math here? Like if gamma is 1, right? It's always like, you add up all the rewards, right? Without discounting it. But if gamma is 0, that means you don't care about future rewards at all. You just want the current best reward. Okay. So that's just like the trade-off. It's kind of like you want to balance. So let's say gamma is 0.5, right? That means you kind of care about future rewards. You kind of don't care about future rewards, right? So it's like a trade-off, how much you want your future rewards to matter. Okay. So it's just something that is quite important. So please take a note of that. And here we arrive at the goal of reinforcement learning. This is like the most important thing in reinforcement learning. Every single algorithm you'll ever read, you'll ever make, you'll ever come across wants to do this. It wants to maximize the expected return, okay, or the return or the total reward you get. Now, what is this E, right? What is this expectation? Why is this E here? Does anyone know like what expected value means? Yeah, go ahead.
It's like if you play many games, it's the hypothetical average return we'll get per game.
Right, exactly. Yeah, that's perfect. That's perfect. Why do we have an expected value here? Because we want to consider average. We don't just want to consider one case, right? We want to take into account all the possible situations that the agent can experience and average them, right? Basically, take account of the average return. You want to maximize that because if you just maximize the reward, the return for one possible situation, what about the other situations that you get terrible return for? All right. You want to maximize the average of all the possible situations here. That's why you have an expected value here. And expected value is quite important in reinforcement learning. We'll see that later. But just keep this in mind. Okay? This is the goal of reinforcement learning. And yeah, I mean, this is exactly what I just said, right? An agent interacting with its environment needs to achieve a goal. And this goal is maximize the expected return pretty much all the time. You go on any paper, any reinforcement learning paper, it wants to do this. Okay. If the agent doesn't do this, it does something else. Usually no one cares. Like you want to do this. Okay. Any questions so far? Decently clear, I hope. I think overall, like at least in the beginning, it's kind of intuitive. I mean, it's just sort of what you would do in your real life. So hopefully it's clear so far. Now, what is this? Okay, now we've been speaking in terms of like abstract all the time, right? Like examples, specific examples, this and that. But we need a more formal definition, right? Like this is what I said, right? We need to have a formal definition, right? Because we can have every example possible, but we need to apply this framework to any decision-making problem. We need a formalism. And there's something called a Markov decision process. Has anyone heard of like a Markov chain? Yeah. Yeah, okay. Some people have. Okay. Okay, it's this. Now, this diagram looks kind of strange, but it's basically what I just said. Okay. Let's start at the top here. You have an agent. Okay. It takes an action, right? It goes here in an environment. Okay. This environment could be, anything. It could be your school. It could be anything, right? But it takes an action in the environment. And the environment switches. It goes to the next state, ST+1, the next state. Remember, actions influence future states. Okay. And also, the environment will generate a reward for the agent. Otherwise, the agent cannot learn without a reward, right? The agent needs to know how good the action it just took in the environment is. This is like the +10, -20, +1 I just talked about in the Bayesian example. Okay. And this just repeats, right? So it's very simple, right? The diagram looks kind of complicated, but it's actually just what I just talked about. And just some terminology here. The agent is said to collect a trajectory, okay, a trajectory of experience across time steps, okay? It's discrete. There's a time step, right? At time 1, I do this. At time 2, I take another action. At time 3, I do this. As you can see here, a trajectory is simply some experience. Just think about that, right? The agent starts in a state, S0. It takes an action, A0. It receives a reward, and it goes to state S1. Right? And it repeats and repeats until the end of the episode or the end of the trajectory. And now this is like the mathematical formulation, or not the mathematical formulation, but just more formal definition, okay? And the reason we want to introduce this is because if you read a reinforcement learning paper, this is in every single reinforcement learning paper that's ever been written. They will write this because you need a formalism to work with. Our Markov decision process is defined by the following tuple. S is a set of states. We're going to assume it's finite for now. It could be infinite. A is a set of actions. Once again, it could be infinite. P is something called the transition dynamics function, a probability distribution that maps and state maps a state and action. I don't know why there's a state here. Maps a state and action to a probability. I'll explain what this means later. R is the reward function, and gamma, if you remember, is the discount factor. These things make up a Markov decision process. Okay, it's what is needed to define an environment, an RL framework, reinforcement learning framework, and you'll see this in every single paper ever. You don't need to remember this for now. Once again, I think it's still pretty intuitive, right? You have states, actions, rewards. Okay, but this is something that needs to be introduced. Quick word on the transition dynamics. We'll go into this transition dynamics in the future, I think in week 2. But basically, it's a probability distribution telling you how the state evolves when when an agent takes an action in a given state. Right? Because you have to keep in mind, when you do an action, the result is not always predetermined. Let's say it's kind of like let's say you throw a paper airplane in a windy environment. There's randomness involved, right? The wind can blow the paper airplane here, there, up, down. There are many possible next states it can go to. And there's a probability that when you throw it, it'll go to one of those next states. So that's all the transition probability definition is, right? If you're in state 1 and you take an action A, keep in mind, right? You need a state and an action to define this, right? You're in a state, you take an action A, it tells you what's the probability that it goes to this state or this other state. So let's take this example. You're in state 1. There's 2 possible next states you can reach after you do an action. The transition probabilities tell you there's a 33% chance that if you take this action, you'll go to state 2. There's a 67% chance you take this action, you'll go to state 3. Okay, is that clear to everyone? Now, a lot of the times, actually, I mean, a lot of my experience, a lot of my work, this thing like is deterministic, meaning that in a lot of our examples later on as well in this lecture and many others, if you take an action, you will 100% chance end up in this particular next state, right? That simplifies the RL problem a bit more because you know when you take this action where you'll go. But in a lot of RL problems, a lot of real world problems, it's not the case. When you take an action, there's a chance you could end up in this state, or any other state. So just keep that in mind. We'll go into this later. Okay. Also, we're kind of ahead of schedule here. So I'll just pause for any questions. No? Okay. Okay, good. That means I'm doing a good job, right? That's good. Yeah, go ahead.
Math-based states, there are too many to compute. Like there, in like real life examples of this, and also like theory-based examples too. But how does a reinforcement always react to there being too many like probabilistic states?
Yeah, I mean that's a really good question, and yeah, you bring up a very good point. I mean, this example is very simple, and examples will cover very simple. But like in a real world, right? Let's assume like you're driving a car, okay? Let's say one of the actions is you apply a torque to the wheel, right? You can end up and the state is like the position along a path, right? The position along the path is not discrete. It's not like 1, 2, 3, 4. It's like maybe 1.5, 1.57, 1.6, right? There's an infinite amount of like states you could go to. And the answer to that is I mean, so that's a very good question. And this ties into the types of RL we'll talk about. There's something called model-free RL, where you learn only from interactions. So it's not like you don't care where you end up, but let's say you're in this state, there's infinite amount of next states. You take an action, you end up at the next state, right? But it's one out of infinitely many states, right? You'll get a reward for that and you can learn from that. And if you do this many, many times, right? Many times, you'll find that although you don't cover the infinite state space, you'll have a very good estimate of where it'll end up next. You get it? It's like an average. Once again, this is why I brought up the concept of averages. If you keep taking this action in this state, you'll eventually find a pattern or a general case, right? Maybe 90% of the time it'll go here or go to this state, okay? But there's also like, there are infinite outcomes, but one is preferred most of the time, for example. That's like how you take care of it. Do you see what I'm saying? Like, a lot of RL uses something called function approximation to do this, but we'll get into that. But yeah, that's a very good question. You have to think about this. Like, in the real world, there's so many possible next states. There's so many possible states actions. Because keep in mind, right? Here it says finite, but that's just for this course. You can have an infinite state space. Think about it. If you're applying a torque to a motor, you can apply 0.1, 0.15, 0.12. There's an infinite amount of actions you can take, right? So yeah, keep that in mind. Do you guys need a break? Like, you guys want a break? Because we can take a break. No? Okay. Oh, we'll finish before 9 o'clock today. Okay. Now, this is probably the most important chapter of this course. Oh, not of this course, of this week, of this lecture. So please focus. Okay, please lock it. Okay. And please ask questions if you don't understand. What's inside an RL agent? Okay. A reinforcement learning agent consists of a combination of the following components: a policy, a value function, and a model. We won't talk about the model today or this course, but the first two you should know, hopefully, like the back of your hand by the time we're done with this course, or hopefully this week. A policy and the value function are two of the most important things in reinforcement learning. A policy is the agent's behavior function, its brain. It tells the agent what to do in a given state. Okay? If I'm sitting down, maybe my policy is to take out my laptop and put it on the desk. Okay, that's a policy. It tells what the agent to do given the following state, the current state, and only the current state. We'll go into this. A value function is the agent's belief of how good each state and or action is. As I said before, if you remember from the K-arm bandit problem, okay, an agent needs an estimate of how good things are, whether it's a state, whether it's an action. Otherwise, how is it gonna know what to improve on? Okay, so these two things are very, very important, and we'll spend the next 30 minutes talking about it. So please, yeah, please, if you don't understand anything here, please ask. You'll be lost for the next course and the next one and in your RL career, for sure. Policy is the agent's behavior or its brain, okay? It determines an agent's action given a state. An agent's policy only depends on the current state. Only depends on its current state. That's a very important assumption in reinforcement learning. What does that mean? So, let's say you're an agent, you're in this state. Let's say you're a trash picking agent in this room, okay? And you start maybe here and you move around, you try to look for trash. You're here, you're like in this corner here. And you need to make a decision on what comes next. What action to do, where to go next. All the information you need to make that action depends only on the current position you are now. It doesn't matter if you have traveled across the room. It doesn't matter of the history, your history of experience. Or it doesn't matter the history of experience you've experienced. That's a sentence. All that is needed to make your action, to do the action, depends on your current state. That sounds a bit weird, but hopefully, yeah, go ahead. Hopefully we'll. It could be, yeah. I mean, a trash picking robot could have many actions. It could be move the wheels to go forward. It could be raise your arm to pick up trash. Yeah.
Where you go next? Doesn't it matter where you go?
Yeah, see, that's what you would think. But in reinforcement learning, a policy, like even mathematically, it's defined only on the current state. That's a key assumption of reinforcement learning. So there are two types of policies: deterministic policies and stochastic policies. Does anyone know what these two words mean, by the way? Yeah.
Same thing every time given the same input.
Oh yeah, perfect.
Stick is like random.
Oh yeah, perfect. So you guys have kind of an idea of what these things are then. So let me just quickly talk about them. A deterministic policy maps a state to one action with 100% probability. So okay, so look, if you see this symbol pi, right, pi of s, in reinforcement learning, this is how we denote a policy. This is the terminology, this is like the mathematical form of a policy, pi. Okay, that's what a policy. And always, like, you know what functions are, right? Functions, right? You have the bracket and you have the input here, right? You input something to a function, you get something out. In reinforcement learning, the input to pi will always be just s, pretty much always just s. There's no st minus 1, st minus 2. It's just s, the current state. Okay, but I digress. So a deterministic policy maps, given this state, it will always take this action. It will always take this action. So an example here, right? Let's say you're in state 0 the policy says, okay, in state 0, always take A1. In state 1, always take A0. In state 2, always take A0. There's no randomness here. If you have a deterministic policy, you see you're in this state, you'll always take that action. Example, let's say your policy, you're trying to solve this problem, trying to get home as fast as possible. This is a deterministic policy because if you're in this bottom left square, okay, you'll always go right. If you're in this bottom right square, you'll always go up. There's no randomness. Clear? I hope that's clear to everyone. A stochastic policy is that multiple actions might be selected with non-zero probability. There's some randomness to the actions. Okay. So let's say there's two states here, S0 and S1. There's 4 possible actions you can do in these states. Okay. Notice that for this particular policy, right? If you're in S0, you'll go up with 60% probability. You will go down with 5% probability. You'll go left with 10% probability, and you'll go right with, I think, 25% probability. Right? So that's random. There's a distribution over actions given that you're in S0. And of course, the probabilities need to add up to 1, right? For each state. And this is just denoting that. The sum over the actions equals 1. The probabilities of taking these actions equals 1. And there should be at least some probability, or 0 or some probability of taking a particular action in a particular state. Okay. And yeah, so this is a stochastic and deterministic policy. And this is the example, right? In some states, so this is the same environment as before, but in some states, right, there's a 100% chance of going right? For example, you're in top left corner, you'll always go right. But if you're in the bottom left corner, there's a 50% chance you go right, and there's a 50% chance you go up. Okay, this is a stochastic policy because it's not, not everything's fixed. So now let me ask you a question, okay? Do you guys remember the epsilon greedy policy I talked about, where you for the slot machines, right? You always pick machine 1, the highest reward, but with some small probability, you pick one of the other machines. Is that a stochastic or deterministic policy? Stochastic? Yeah, okay, perfect. Okay, we get it. Okay, good. Okay, before we get into this value function, which we'll spend the rest of the time on because it's that important, we're gonna take a break. Okay, 10-minute break, it's been an hour. Let's reconvene at like 8:08 or something. Feel free to, take a break. I'll be here. Feel free to ask me any questions if you need. Yeah, we'll take a quick break. Okay, so just a quick thing about the policy again, right? I got a question about like the history thing. It's kind of weird that like a policy doesn't need to include past states to make the current decision for its action. It only depends on the current state. This is more of a, like, don't get hung up on this, is my point. This is more of a mathematical thing that helps out with the math in Markov decision processes and proofs, okay? In practice, you can define anything to be your state. You include whatever information you want. If you're a trash collection robot in this room, you can define your position, you can define the air quality, you can define the whatever, okay, to be part of your state. You can even define the history of your past states as part of your state. So it's kind of like it's more of a mathematical formalism than a rigid like thing. Right? So I didn't even make a slide on it. Just keep that in mind. Because all works in Markov decision processes. The term Markov, what is Markov? Markov is a dude, but in math, right? The Markov property is that the probability distribution that depends only on the current state. Okay, like that's the Markov property. You can look it up. It's like that's why we need this. Okay, moving on to the value function. Now this is one of the more confusing things when I first started out with RL, but it is absolutely like critical that you understand this. A state value function is a quantification of how good or bad a particular state is. It sounds simple enough, but let me continue. It's defined as the expected return starting in a particular state and following policy pi. It's a number, 1, 2, 3, 4, 6.5. It's a number that tells you how good a particular state is. Now, this looks pretty familiar, right? This equation, right? It kind of looks like the total return, right? RT plus 1 plus gamma RT plus 2. But notice there's a line here. It's given ST equals S. Given the current state, okay, what is the total expected return? And notice there's a subscript on the V. By the way, V is how we denote this, okay? V is how we denote this. There's a subscript of pi on the V. What is pi again? The policy. So for a given initial state and a given policy, you have a value function. If the policy or the state changes, you have a different value function. There are going to be examples of this, but yeah. This is something else. This is also another critically important concept, which we'll get into next week. Today, we're going to focus on V, right? The state value function. This is called the state action value function. It's very similar to a state value function, but it's a numerical quantification of how good or bad a particular state and action is. Notice, it depends on pi as well, the policy. It's QS comma A. This is V of S. Okay, so it depends on the action as well. It's the expected return from this state given this state and action. This is not the same as V pi of S. We'll get into this. You don't need to remember this for this week, but this will become critically important in future weeks. For now, we're going to talk about the state value function. Okay. Why value functions? I will talk about this later, but this is just an idea. Okay. I mentioned before that an agent needs an estimate of how good things are. And one of the things that an agent should be able to estimate is how good the particular state is, how good this state is. But think about this for a minute. Like, you're an agent, you're in this state, and you take actions. You can take many actions. From those actions, you can go to many other states. And then from those states, you can go to many, many other states. So, I mean, like, let's say you're an agent in here, right? Here are all of the states you can go to, all these circles, right? But let's say you go to this one after taking action. Then you can go to all of these states, but let's say you go to this one. And you go to all of these states, et cetera, et cetera, et cetera. There's so many things in the future you don't know about, what state you'll go to. And there's randomness involved, remember. Remember the transition probabilities, right? If you have a random chance of going to different states, then there's so many like things involved. The value function summarizes all of that information, all of that complexity into one single number. Okay, it's kind of like an oracle. It's like the best thing ever. Think about it. Like everything this agent could possibly know in the future and go to in the future, all the rewards you'll get, it summarizes into one number, just a number. If one state has a higher value than another, you know it's better than another. So if state 1 has a value of 115 and a state 2 has a value of 110, state 1 is better than state 2, period. You don't need to think about, okay, but what if, like, in state 1, it transitions to a bad state, or like in state 2, it transitions to like a better state or whatever. If I am an oracle and I tell you that state 1 has a value of 115 and state 2 has a value of 110, state 1 is better than state 2, period. Because this number here, this value, already took everything into account. It already accounts for all the bad places state 1 will go to, and the bad places state 2 will go to. Sounds kind of magical, I know. Like, kind of like, wow, like if we have this and we can solve all our problems. And yes, actually, if we have this. The goal of a lot of RL is to estimate the value, the correct value. So does that ever make sense? A sort of future like summarization point. Okay. This is just a model. This is out of scope, but just quickly addressing it. It's basically an agent's representation of environment. Because let's say you're an agent interacting with some environment, right? You might want to build an internal replica of that environment so you can use your own environment instead of interacting with the actual one. Why would you do that? Because let's say deployments, like interacting with the environment, is very expensive. Let's say you want an agent to, you're training like a Mars rover to go on Mars. In regular RL, do you want to spend like $10 billion to put your Mars rover on Mars and have it explore around Mars and it crashes and you lose all that money? No, it's very expensive to interact with the real environment. So sometimes it might be better to build an internal model so you can work with it internally rather than interacting with the real environment. Think about like this is basically like kind of like building like a replica or a simulation, working a simulation kind of. Okay, makes sense? This is out of scope of this course, but just know that there's something called model-based reinforcement learning, where it's all about using models to do reinforcement learning. Now back to the value, okay? So this is very important. I want you guys to like just think about this like all the time. Okay. We're gonna do an example now. I think the policy will be clear, model will be clear. The value is where I want you guys to like think about. Let's say you have this environment, it's a maze. Okay, you wanna start at the start and end at the goal. The rewards are -1 per time step, meaning that every like second, every time step you remain in a maze, you're getting penalized. You want to get out as fast as possible, right? The actions you can do in this maze at every state is you can go up, down, left, or right, north, south, east, or west, okay? And the states are the agent's positions in the maze. So, I mean, if the agent is here, then this is its state. If it's here, this is its states, okay? So this is the environment we have. Now, this is what we call an optimal maze policy, optimal policy. What is an optimal policy? An optimal policy is the best policy for this environment, right? Meaning, what does that mean? It means it achieves the highest expected return, okay? If you follow this policy, you'll get a good return, the highest return, better than any other policy. Why? I mean, it's pretty evident, right? It's like making a beeline for the goal. I don't see that. Does everyone get what the optimal maze policy is? I think it's pretty straightforward. Now, here's the optimal state value function. Okay. Recall that the value function is an agent's estimate of how good a particular state is, starting in that state and following that policy. So here we have fixed the policy to be the optimal policy. This is the policy we're following, okay? We fixed that. Now, it just depends on the starting state. If you're here at the goal, you take one step and you're out, right? Because the policy tells you to take this step. So you take one step and you're out. That's why you get a -1 reward. Return, rather, value, sorry. If it's -2, it means that you'll take 2 steps and you're out. So the value is -2, and so on and so forth. This is the value function. Let me repeat this again. This is the value function for the optimal policy. Value function depends on policy. I'll show another policy later. It will have a different value function despite the environment being the same. Does not understand that? This is the value function for the optimal policy. And the value changes in every state because the value V of S depends on S, the state you start in. Okay. Now, this is a bad maze policy. You'll never escape. You're trapped forever in this maze. This is another policy. Actually, let me just, what type of policy is this? Deterministic or stochastic? Okay, great. Yeah, okay, good. Just check it. What is the value function for this? Can someone give me like just a guess? Sorry, it's okay if it's wrong. Let's say you start in this state here in the top right. What is the expected future return you'll get? Remember, you'll never escape the maze, and you get -1 per time step you stay in the maze. What is the value of this state? Yes, precisely. In every state, the value is -infinity. So I mean, okay, I kind of just did the exercise. But so what is the value of this state? This highlighted state. Yeah, -infinity, right. Notice, the environment did not change. Only the policy did. The policy went from being the optimal policy to a really terrible policy. And the value function has completely changed. Once again, the value function depends on the policy. Okay, does everyone understand that? Okay. Now here's another policy. Okay, it's it's a policy, but notice at this state, there's a 50% chance of going right and a 50% chance of going down. But notice this: if you go right here, you'll never escape the maze. But if you go down here, you get out. First of all, what type of policy is this? Stochastic. Okay. Now, what is the value of this top right state? -infinity. Okay. What is the value of this state right here? -3. Okay. What is the value of this state here? Now, okay. The value is the expectation, right? It has to take into account all future possible scenarios. There are two scenarios that can result from being in this state, right? Remember, this is a different policy now. And once again, notice the value function has changed, right? This side is negative infinity. This side, it's like actually good, right? Once again, the value depends on the policy. I'm gonna repeat that again so you can remember. But for this state, you have to consider all possible outcomes. In every other state, there was only one outcome, right? Because if you go, yeah, you get it. But in this state, there's two possible outcomes. You have to consider both outcomes. So guess what? So the policy, you have to take the expected value. So I hope everyone can understand this. The value at this state is equal to 0.5 times -6. Why -6? Because if you go down, right, remember there's a 50% chance of going down. If you go down, you'll escape the maze in 6 steps. So the total return you'll get is -6. However, if you go right, you'll never get out, and your value, your total return, will be -infinity. So the value function, having to consider both of these options, all right, you take the expected value or the average. You do 0.5 times -6 plus 0.5 times -infinity is -infinity. So the value here is still -infinity. Is that clear to everyone? Okay, once again, to kind of summarize, the value depends on the policy and the starting state. Okay, every state has a different value, and the value has to consider all possible future situations. Okay. So value functions. Okay, value functions are the total expected return an agent obtains, starting from initial state and following a policy afterward. It captures all future rewards, taking all the randomness into account. It depends on the starting state, it depends on the policy, and it depends on the transition dynamics of the environment. What do I mean by that? Notice that before here, right, in all these situations, all these like policies, or rather in this environment, right, let's go back up. The actions are north, south, east, and west. If you take an action here, right, and you go up, there's a 100% chance you'll end up at the adjacent top right state. That means that the transition dynamics here are deterministic. There's no randomness. But what if, let's say, for example, you have the same environment, but at this state, there's like a teleporter. Like it can teleport. Let's say you go right, you transition to here, okay? And you go down, or you decide to take the down action, okay? There's a chance you end up here, but there's also a chance it teleports you straight to the goal. There's a chance it teleports you to here. There's a chance it teleports you to, I don't know, Ottawa or something. This would be an example of environment where the transitions are stochastic. And you have to take into account that value as well. Now, I haven't done it here, but let's just think about this for a second. Let's say we want to find the value of this state again, right? But keep in mind, there's a teleporter here. Here, we did 0.5 times -infinity because we know that if we go right from here, the value will be -infinity because there's no random transitions. You'll never escape the maze. But in this case, okay, if you go right from here, and let's assume the policy will take you like here, you can no longer just simply do 0.5 times -infinity because there's a teleporter here. You have to consider that as well. You have to take that randomness into account. Like, what if it teleports you to the goal? What if it teleports you to... So that just becomes wildly more complex, right? Because for every state along this path that can possibly end up at the teleporter, you have to consider the randomness of the teleporter in the value function, because the value function has to consider all future options. So this is why the value function is so hard to estimate. It's so hard to understand and estimate and get. Because in the real world, in many cases, the environment could be infinite. it could be random. So you have to, so imagine a tree, that's like another branch of the tree you have to go down, right? Like it's this, right? In our case, it was just one path. But since there's a teleporter amount, there's another tree, like there's another branch you have to go down. So value functions are powerful, but they're complex to estimate. They're hard to estimate because you need to consider everything in the future. I know I sound like a broken record, but it's just so important that I have to say it again and again. And finally, to wrap it up, this is a model. It's a maze model. So this could be, let's say the like 10, maybe the agent has been exploring the maze for like 5 minutes, or has done like 1,000 transitions, 1,000 time steps. And this is its like current guess of what the environment looks like. Okay, it's not perfect, right? It's not perfect. But it's a guess, right? The agent's internal guess of what the environment looks like. And notice the agent can use this model to actually already find the optimal policy for this state, right? Can already find optimal because it's reached the goal. And notice another thing, that part of the model involves the rewards at each time step, right? If you have a model, you can't just model like the physical like model of the environment. Like let's say you're doing a trash robot, you can't just have a model of where the chairs are, where the tables are, where the stairs are. You also need to model the reward. Because when you're using your own model to do planning and to like understand the environment, you need a reward as well. Here's another value function example. And this is like the last thing we'll do today, but we're gonna end on the value function. Let's say you have this environment now, okay? This is a grid world. By the way, if you do RL, you're gonna get comfortable with grid worlds. There's like, everything's a grid world. There's rewards of 0 for any transition. So let's say, you go here to here, here to here, it's 0. However, if you transition from A, like you take any action in A, you'll always go to A prime, this state down here, with a reward of +10. If you start in B and you take any action, okay, you will always get +5 reward and get to state B prime. If you're near the walls and you take an action that bumps you into the wall, you'll bounce back, right? You'll end up in the same state, but you'll get -1 reward, so you don't want to be near the walls. The actions are once again, you can go up, down, left, and right. And the states are the agent's location in the world. And finally, the transition dynamics are deterministic. There's no like teleporter. Like if you go right, if you're in this state and you go right, you'll definitely end up here. You won't like teleport off to somewhere. There's a 100% chance you'll go where you want to go. Notice how much stuff I just had to say to specify it. Oh, wait, I haven't finished. The discount factor is 0.9, meaning if you take 10 reward here and you take another step and you get like -1 reward, you bump into the wall, that -1 is multiplied by 0.9, if you recall the discount factor equation. Notice how many things I just had to say to specify this environment. Why did I have to do that? Because I'm following the formulation from Markov decision process. Remember what a Markov decision process is: states, actions, rewards, transition function, discount factor. Yeah, right? You need all these things to specify a reinforcement learning problem. Okay. Now we have to do even more because, as I said before, I might have said this once or twice, but value function depends on policy. So you have to specify what the policy is. Let's say for this policy, we're going to use a uniform random policy, meaning you go up, down, left, right with equal probability. Okay. So once again, this is a stochastic policy. And I'm just going to tell you, let's say I'm an oracle, that this is the value function. Okay. This is the value function. Like you might think, okay, how did you find that? We'll get into that. We're not going to cover that right now. But let's just say somebody told you that this is the value function for this policy, for this particular policy. Okay. Now let me ask you, what is the best state on here? Where do you want to be? What's the best state? A, right? Okay. What's the worst state? Bottom right, exactly. Remember, if you're given the value function, the bigger number is better, right? No need to overthink it. All right. And you might think, well, this environment is so complex. Like, what if you bump into a wall and it's random policy, right? What if you move here, here, here? Once again, this number summarizes all of that. Everything is summarized. And to give you an idea of that, you might notice something interesting here. Okay. A gets plus 10 reward, right? I mean, that's a pretty high reward, plus 10 reward. But its value is lower than 10. I mean, that's, I guess, kind of strange, right? B is plus 5 reward, you get plus 5 reward, but its value is actually higher than 5. Now, why is that? So let's think about, let's take a closer look at the value of A, right? Where do you end up after you get out of A? You take, remember, you take any action in A, there's a 100% chance you'll end up in A prime. You end up here. Now, what is it about these like last rows? Like why, like what's special about them? Like what, do you want to be there? Like, is that a good state to be? No, right? Because according to the random policy, remember the policy is random, you'll be like bump into walls all day. Now there's a chance you can make it back up, but you have to get really lucky, right? You have to get like 0.25 to the power of like 5. That's a chance to just get up there, right? So why is the value of A bad? Because the value function takes into account all future rewards, even though the immediate reward is plus 10, because you land in a terrible spot, the value will reflect that. It will be lower than 10. Now, of course, you know, since you get plus 10 reward, it's still very high, much higher than the other states, which is 0 and B. So of course, it's still the best state to be. But it just goes to show the power of the value function. If you have the value function, you can just say, okay, A is the best because it takes into account the future rewards. Okay. But it's the future, but the value is lower than 10 because you end up in a bad spot. Okay, so now what about B, right? B has a higher value than its reward, right? Because it's plus 5, right? But notice where you end up in B, okay? This spot is much, much better than A prime because you're much closer to B and A again, right? You can easily, well, I guess, yeah, it's around same distance to A, but you can make it up to B pretty easily. So once again, the value reflects this. Even though the immediate reward is only 5, because you land up in a good spot and you have a higher chance of going back to the better places, the value will be reflected as such. It will have a higher value. And yeah, I think that's it for this week. Oh, never mind. Sorry, got ahead of myself. So does that, I mean, this is the last slide, but does everyone understand value functions? Why they're so powerful? That means what does a value function depend on? And the starting state, right? The starting state and the policy, right? The value function changes based on. I might have made okay. Someone said transitions. Yes, it does. Like yes, but and no. Like the transitions make it harder to calculate the value, but it's not like, let's say the policy and the starting state remain the same. If the transitions actually, I guess no, never mind. No, it does also depend on the transitions. Yeah, sorry. Okay. Okay, so final slide. So classifying RL agents. Now, as mentioned before, RL agents may contain a mixture of a policy, a value function, and a model. Okay. They're value-based RL agents, meaning they contain just the value function and no explicit policy, right? Now, why would they not have a policy? Like, why is it that only having a value function might be enough? Because you already know which states are good, right? Like, I mean, if I have this, right, this value function, I already know A is great, right? But then again, there's a lot of intricacies here, which we'll get into next week. This is a very misleading sort of heading. I don't know why I wrote it like that. But anyways, there's policy-based, explicit policy, no value function. But the most common you'll see, I'm pretty much all, I guess like pretty much all our algorithms, like the good ones, the popular ones, are actor-critic. You have a policy and a value function, and we'll get into why it's called actor-critic later. Okay, and also models. There's a model-free reinforcement learning, meaning you can have a policy or value function, but there's no model. But you can have a model-based reinforcement learning, meaning you have a policy and a value function, but there is a model. Now, why would you have a model-free one? Because like I mean, obviously having a model is better, right? Like you can. So why would you like have a model-free version? Go ahead.
It takes up less resources.
Yeah, pretty much. I mean, think about trying to model, like, let's say the weather. Let's say you want to build an agent to do the weather. How are you gonna do that? Like with some like neural network, like with some like 4-layer neural network, it can model like the weather. No, you need a huge, maybe even like a huge model, so sometimes it's just not worth it to get an accurate model, because if you have an inaccurate model, your predictions will just be terrible. But on all basis, once again, if you're like trying to deploy on the moon or something, you can't just always test on the moon, right? You'll have to need to build a model and test it locally. Okay, that's it for this week. Thank you guys for coming. If you want to check out more UTMIST events, if you like this workshop, there's many others like it. Please go on the link tree. There's, oh my God, there are like so many like events. You won't even believe how many events there are. And there's a feedback form. Please let me know how I did, if the slides were too confusing, if I went too fast, too slow. Yeah, just give me some feedback so I can prepare for next week and the week after. And please do come, okay? It only gets better from here. Thank you.